Let's take a look at some material. And we don't have time to cover all these topics, so I'll just kind of bounce back and forth between different ones. Not back and forth, but from section R.1 on, just hit certain topics. A lot of things in section R.1 you probably won't have trouble with, but let's talk about the order of operations. This is when you work across a math problem, specifically with all the numbers. What do you simplify first? And this is based upon, please excuse my dear Aunt Sally. Now, first letter of each tells us what to do. This is PEMDAS. You have heard it referred to in that form. The P stands for parentheses. So you do what's inside the parentheses. Now that doesn't say you get rid of the parentheses. That may occur, but you do what's inside the parentheses. The E stands for exponents. My dear is multiply or divide as you encounter either one from left to right. Aunt Sally, you add or subtract well, we'll get there eventually, as you encounter either one from left to right. Let's take a look at an example. We got 6 divided by 3 to the third power times 2 divided by 4. Yeah, that'll work. Please do what's inside parentheses. Here's 6 divided by 3. That's going to give us 2. So we got 2 to the third times 2 divided by 4. Excuse, please excuse, exponents. So we'll do this 2 to the third. That 2 to the third means 2 times 2 times 2, which is 8. Everything else carries down. Please excuse my dear. Multiplication or division is encounter either one from left to right. Well, our first multiplication or division from left to right is 8 times 2, which is 16. And then our last item, we got 16 divided by 4, which gives us 4. And that would be our answer. Now, before I leave this section, let's talk about square roots. I have another college algebra class that's really struggling with the square roots, and I thought, I don't typically cover it, but maybe I better mention how to simplify a square root. This right here is a square root, and if we do the prime factorization, the primes are 2, 3, 5, 7, 11, sometimes 13. There's actually an infinite number of primes, but almost 95% of mathematics seems to come from these first numbers. So we start with 20, we do our tree breakdown, and we look for if we start with the first prime, so we're looking for a number that divides into it. And we ask ourselves, 20 is divisible by 2, and it is. 2 times 10. When we say divides into it, if you put in your calculator, if it doesn't have any decimals. Or, just integer-wise, if you can think of another number you can multiply times that one, that'll give you this original number. Now 2 is prime, so we circled it. Now I'm still on my first prime, 2. And 10 is divisible by 2, 2 times 5. 2 is prime, so we circle it. 5 is prime, so we circle it. So we'd have 2 times 2 times 5. Now with the square root, we're looking for a pair of somethings. Here's a pair of 2, so a pair of 2 is going to come out in front as a single 2. And our answer is 2 square root of 5. Now while we are looking for a pair, it has to do with our index. Index is whatever number's in this little slot right here. And if you do not have a number, by default it's 2, square root. So if I had a different problem, that was a cube root of 54. Well, we're going to do a prime factorization breakdown. So we got 2 times 27. We were on the first prime, 2. Now 27 is not divisible by 2, so go to my next prime, which is 3. And it's divisible by 3. 3 times 9. 3 is prime, so we circle it. And then 9 is 3 times 3. And both of those are prime, so I circle them. So we're going to have 2 times 3 times 3 times 3. Now our index is 3, which means we're looking for a set of 3 of something. In this case, we have 3 3s. So they're going to come out in front as a single 3. And our answer will be 3 cube root of 2. Grab a drink here. And let me clear this off. Okay, that pretty well sums up R1. So let's go to R2. And this talks about some terms and coefficients and so forth. Probably won't focus too much on definitions there. I'll go directly to simplifying algebraic expressions. Now an algebraic expression, that's where you have something like 3x minus 2y over 5. This is an algebraic expression. Algebraic expression has variables involved in some manner. That's pretty vague, isn't it? But it really is that vague. This is an algebraic expression. 7x is weird as it seems would be an algebraic expression. So there's some kind of math operation being done, and you got variables. Technically, x would be an algebraic expression. That's 1 times x. Now, some things we do with algebraic expressions is we evaluate them. So let me show you an example. We're going to evaluate, actually I can show that example right there, 3x minus 2y over 5 for x is equal to negative 2 and y is equal to negative 1. Now evaluating an algebraic expression, step 1, replace all variables with sets of parentheses. Step 2, plug in the given numbers in the appropriate parentheses. And step 3 is to simplify. Over here, when they say simplify algebraic expressions, that typically means where you've evaluated. Then you want to simplify it from there. Now there's other simplifying we're going to see throughout the entire course, actually. Because remember, algebraic expression is pretty vague. It covers a lot of different cases. Okay, so let's look at this one. Step 1. replace all variables with sets of parentheses. So I'm going to go to my 3x minus 2y over 5, and everywhere I have an x, I'll put parentheses. Everywhere I have a y, I'll put a parentheses. Step 2, plug in the given numbers in appropriate parentheses. So where our x was, we're going to put a -2, and where our y was, we'll put a -1. Well, we got 3 times -2 is -6. -2 times -1 is a +2. Although I didn't say it, well, this is step 3. Although I didn't say it, this right here is the order of operations. And when you have a fraction, you do the top part separate from the bottom, and then you handle the fraction. So -6 plus 2 is -4 over 5. Now I handle the fraction, but there's nothing to handle. That would be our answer. So that's evaluating. Now there's another type of simplification we're going to do at this point in time. It's called the distributive property. And it looks like this. We've got 5 times x minus 7. When you've got a single item out in front here, after you read the definitions, that'd be a single term. But it doesn't have to be a term. It could be a single radical. It can be a single item, basically. There's no pluses or minuses. You just got that single item. Then you can use something called the distributive property, which means we'll take the 5 times x and 5 times -7. 5 times x is 5x. 5 times -7 is -35. And that would be our answer. So that's the distributive property. Now R.3. Integer exponents and scientific notation. So we're going to review on this. We've got our properties of exponents. And one of them says if you got x to a power, x to the m times x to the n. So you got x to a power times x to a power, you add the exponents. For example, if I had x to the 5th times x to the 3rd. Since they're both x to a power, they don't have to be x's, they can be anything. You could have y to the 5th times y to the 3rd, or you could have 2 to the 5th times 2 to the 3rd. It doesn't matter, as long as these are exactly the same, then what you're going to do is you're going to add the exponents. So we've got 5 plus 3, and we'd have x is 8, or x is 8. Now we have another property. It says if you got a x to a power being raised to another power, then you're going to multiply the exponents together. For example, if I have x to the 4th being raised to the 10th power, we have one exponent being raised to another exponent, so you're going to multiply the exponents. So I got x to the 4 times 10, which gives us x to the 40th. Now x to the 0 power. Anything to the 0 power is always equal to 1. So it doesn't matter how bizarre it looks. Maybe it's something you've never seen before. It's a little bit of trig, smiley face thrown in. Doesn't matter what we have. Anything to the 0 power is always equal to 1. Now if you're wondering, well, why is that? If I look at 4 squared, 4 squared is 16. 4 to the third is 64. 4 to the fourth is 256. 4 to the first is 4. Now going upwards. 4 times 4 is 16. 16 times 4 is 64. 64 times 4 is 256. Going backwards, dividing. 256 divided by 4 is 64. 64 divided by 4 is 16. 16 divided by 4 is 4. 4 divided by 4 is 1. So just by the definition of the exponents, anything to the 0 power is always equal to 1. Let me clear this off. There we go. Now there's negative exponents, and the property, let me show you officially what property says. We got x to the negative m, that's going to equal to 1 over x to the positive m. But let's just talk generally, how do we handle a negative exponent? Okay, negative powers, negative exponents. Take whatever is to the negative power opposite of where it is located in a fraction and change the sign to positive. So take whatever is to the negative power opposite of where it's located at in a fraction and change the sign to positive. For example, let's say I had this problem right here, 1 over x to negative 2. We never want negative exponents, so we're going to take it opposite where it's at in a fraction. So you take this x to negative 2, move it up on top. When you move anything where it's at in a fraction, the sign of the exponent changes, so it becomes x to the positive 2. And there's nothing left down below here, so I put a placeholder of 1. You never have blank in a fraction. You always, if you have what looks like a blank, you should put a 1 there. And then x squared over 1 is x squared. On the other hand, if you got x to a negative power, it's not in a fraction. You can always create a fraction by putting it over 1. And then we're going to take the part with the negative exponent, opposite of where it's at in a fraction, so we'll take that down below. You take anything opposite of where it's at in a fraction, and sign of the exponent changes, so it becomes x to the positive 8. And we got blank here, so I'll put a 1 placeholder. Now, if we have a fraction to a negative power, what we do is we flip the fraction, take the reciprocal, and change the power to be positive. And then you would handle it however you would want from there, whatever's appropriate for the problem. Let's grab another drink here. Okay, let's take a look at an example of that. We have x over y to the negative 3 power. We never want negative exponents, so what we do is we flip the fraction. This becomes y over x. That's reciprocal. Reciprocal means fraction flipped. And change the sign of the exponent to positive. So I become a positive 3. Now this should be called, it's not, but it should be called a distributive property of exponents. And it says if everything inside the parentheses is either multiplication or division, and you're raising the parentheses to a power, then you can take everything inside the parentheses to that power. Okay, if everything inside the parentheses is either multiplication, division, you're raising parentheses to a power, then you can take everything inside the parentheses to that power. For example, if I have x squared y to the third power, you notice how everything is either multiplication or division inside the parentheses. We've got x squared times y. So what that means is we'll take the x squared to the third power and the y to the third power. So we'll have x squared to the third, and we'll have y to the third. Well, when you raise one exponent to another exponent, you multiply them together. So 2 times 3 is 6, and this gives us y to the third. Now over in this this problem here, I didn't finish it, but everything inside the parentheses is division, y divided by x. So we're going to take the top to the third power, and we'll take the bottom to the third power. So we're going to have y to the third over x to the third. And that'd be your answer. Now this is oftentimes listed as a property, and I'm not going to list a property. I'll talk about how to handle division. Division where you have x to a power over x to a power. They do not have to be x's. You can have y's. You can have anything, just as long as they're exactly the same. What we do is we subtract the smaller power from the larger power over on the side. Step 2, you have x to the power from step 1 where the larger power was located, and a placeholder of 1 in the other location if necessary. I'll show you the actual property after we get done working a problem with this. This would be if you got x to the 7th over x squared, for example. We have x to a power over x to a power. So subtract step 1, subtract smaller power from the larger form, the larger power. I would say autocorrect got me, but I'm not very good at grammar on some of these, so I have to read it again. See this? Okay, I need to change that. Subtract smaller power from large power over on the side. So we'll do 7 minus 2, which gives us 5. This is step 1. And then step 2 says you have x to that power from step 1 where the large power is located. So we have 5 here, so we're going to have x to the 5th where our larger exponent was, which was on top. And then a placeholder of 1 in the other location if necessary. We have a blank down here for the fraction, so we'll put a 1 there. And x to the 5th over 1 is simply x. Now you may have multiple items, like x to the 3rd, y to the 7th, over x squared, y to the 12th. Oops. I meant for this to be an x squared. Well, we have x to a power over x to a power. So for the x's, I subtract a smaller exponent from a larger one. 3 minus 2 is 1. And we're going to have x the first where our larger exponent was, which is on top. Now for the y's, we'll subtract the smaller exponent from the larger one. So we've got 12 minus 7, which gives us 5. So we're going to have y the fifth where our larger exponent was, which is on the bottom. And there's no need to put 1 for any placeholder because there's no blanks on top or bottom. So that gives us x over y to the fifth. Now the official property for that says if you have x to a power over x to a power, you subtract the exponents. And that's kind of what we did. We just then made a determination of whether it went on top or the bottom of the fraction. Let's see. Simplify zero negative exponents, properties of exponents, scientific notation. I won't cover that. We just have limited time. Now, having said that, I do put YouTube videos out for you to watch. So these topics we don't cover, then you can go out there and see them in a lot more depth. Or even the ones we cover where we just have time for just one example, you can go out there and see many more examples. Okay, rational exponents and radicals. Let me clear this off. And it's best shown by an example, I think. Cube root of x to the fifth. Now this is radical form. And they're specifically talking about rational exponents. So rational exponents. Now I can rewrite this as x to the 5 over 3 power. Now rational exponent means fractional powers. And how it works is whatever power's inside here always goes up on top. If there is no power, then by default you put a 1 up on top. The index, whatever number is in that slot, is what comes down here to the denominator. Now if I have this, we got square root of x. Well, there is no number in this slot, but it's by default 2. That's a square root. So we'll put a 2 here to handle that. Now here we have x and there's no power, but if I were to put 1 here, you could always put the first power. So then this becomes x to the 1/2. Again, whatever power's here goes up on top. And whatever number's in the slot, that's your index, is what goes down below. Now we're going to put that back into radical form. So let's start off with x to the 3/7. And this is going to be the 7th root of x to the 3rd. How it works is whatever number is on top is your power, goes right there. Or we can see it can equally go on the outside of a set of radical. Then whatever number's in the denominator here, on the bottom, that's your index. That goes right here. So that would be the 7th root of x to the 3rd. We're going to find sometimes it's easier to put it back into fractional power form to solve problems. Sometimes it's easier to work with radicals. And this talks about simplifying radicals, evaluating nth roots, and so forth. Let me clear this off. Now the first thing, evaluate nth roots. We already looked at one of these. But let's say I'm going to evaluate the 5th root of 128. Well, we need to do our, actually let me throw, so we need to do our prime factorization. Start with our first prime 2. It's divisible by 2. 2 times 64. 2's primes, I circle it. 64 is still divisible by 2. 2 times 32. 2's prime size circlet. 32 is still divisible by 2. 2 times 16, 2's prime size circlet. 16 is still divisible by 2. 2 times 8, 2's prime size circlet. 8 is 2 times 4, 2's prime size circlet. And 4 is 2 times 2. So we got 1, 2, 3, 4, 5, 6, 7. Yeah, so we got 7 2's. 2, 3, 4, 6, 7. Okay. Now our index is 5. Number in the slot right here. So it means I'm looking for 5 of something. In this case, I got 5 2's. So those 5 2's are going to come out in front as a single 2. And we're left with fifth root, and 2 times 2 would give us 4. We can't bring them out unless there's 5 of them. So that would be our answer. Now it gets kind of tedious if you got a lot of variables. So let's talk about those. Got third root of x to the 13th, y to the 21st. I could write out 13 x's and 21 y's and then figure it from there, but there's a shortcut for it. If we come out here for our x's, we're going to take the power that's on the x, which is 13, divide by our index. The index is numbered in a slot, so that's 3. And this is old style division, so that gives us 4 with remainder of 1. Now this 4 tells us how many are coming out, and this 1 tells us how many are staying in. And we'll talk more about that here in a minute. And then do the same thing with 21. So for our y's, I got 21 divided by 3. That gives me 7 with remainder of 0. The 7 is how many is going to come out, and the 0 is how many is going to stay in. Which means, it tells me I'm going to have 4 x's come out. It's right here. This tells me I have 7 y's come out. And we're left inside 1 x and no y's. So that just gives us single x. In some cases, you have to worry about whether the variable that's coming out of a radical is positive or not. But when you're talking about an odd index, it doesn't matter. If you have an even index and you bring in a variable out and you're not sure it's positive, you put absolute value bars on it to make sure it's positive. Let me look at one more of those. We got square root of x to the 201, y to the 50th. Well, my index, remember, it's whatever number's in a slot. And if there is no number, it's by default 2. So I'll come over here for our x's. We'll take our power, which is 201, divide by our index, which is 2. And that gives us 100 with a remainder of 1. So this is how many x's is going to come out, and this is how many x's is going to stay in. So then for our y's, we'll take our power, which is 50, divide by our index, which is 2, and that gives us 25 with a remainder of 0. And this is how many comes out, and this is how many stays in. Okay, so for this problem, we're going to have x to the 100th come out. We'll have y to the 25th. We had 100 x's come out, 25 y's. Now here we have 1 x left inside, but here we don't have any y's left inside. So that would be our answer. Again, if I was worried about whether the variables are positive or not, if the instruction doesn't say so, you can put absolute value bars around the variables that come out, and then you're covered. Okay, let me clear that off. Now simplifying expressions of the form a to the 1 over n. So if I had, for example, 16 to the 1 over 2. That's what this is saying. A to the 1 over n. So 1 over a number. We have a hard time working with it in this form, so you put it back in the radical form. And this is what it looked like. Whatever number's in your denominator, that's your slot. That's what number goes in your slot. That's your index. And whatever number's up on top here is your power, and that's what goes inside. Well, I know that's simply the square root of 16. And 16 is 4 times 4, which would give us 4. And that would be our answer. Now in your calculator, 16 to the 1/2. You want to make sure you're not in graph mode, so do a second mode to exit out if you've got a TA3, TA4. And we've got 16 to the 1/2. Now I'm going to do a 16 caret, and here's a trick. If you got more than a single number or a single variable in your exponent, you have to put parentheses around it. So I'll put a beginning parentheses, 1 divided by 2. You can put a closing parentheses at the very end if you want, but this isn't necessary. And then press enter. And we get 4. Now simplifying a number to a fractional power, rational exponents, where the numerator is greater than 1. Step 1. Put the number in the numerator of the exponent on the outside of a set of parentheses. Step 2, rewrite what is inside the parentheses in radical form. Step 3, simplify the radical. Step 4, simplify what's left. And what I'm talking about there is if you had something like this, 8 to the 2/3 power. That's different than this previous problem because we don't have a 1 up in the numerator of the exponent. Step 1, put the number in the numerator of the exponent on the outside of a set of parentheses. So that 2, I'm going to put on the outside of a set of parentheses. So we got 8 to the 1/3 to the 2nd power. Now you may wonder, well, where's that 1 come from? Well, when I take the 2 and put it on the outside of a set of parentheses, we have a blank up in our fraction. Remember, we never want a blank in our fractions. We put a 1 there. Step 2. Rewrite what is inside the parentheses in radical form. So this would be the cube root of 8 to the 1st. Remember how it goes. Whatever number's right here, that's your index. That goes in the slot. And whatever number's right here is what goes as your power right here. So that's simply going to be the cube root of 8 to the 2nd power. Step 3. Simplify the radical. Cube root of 8. Well, 8 is 2 times 2 times 2. Now our index is 3, which means we're looking for a set of 3 of something. Here's 3 2's. So those 3 2's going to come out in front as a single 2. And then step 4 is simplify what is left. Well, 2 squared gives us 4. Now the trick, if we were to plug this straight into our calculator, is anytime you have more than a single number or a single variable in your exponent, you put parentheses around it. So we'll put 8 caret, and then beginning parentheses, 2 divided by 3, closing parentheses, and then enter. And that gives us our 4. Let's see. We looked at simplifying radicals. Simplify expressions with rational exponents. Let's talk a little bit about that. After I grab a drink here. sometimes you may have fractional powers, rational exponents, and you need to simplify them. And they follow the same properties as the regular exponents. If we have x to a power times x to a power, remember we add our exponents. So we're going to have x to the 1/2 plus 3/2. 1/2 plus 3/2 is 4/2. And 4 divided by 2 is 2. So our answer would be x squared. Sometimes you have to get it out of radical form, put it in a fractional power form, work with it, and then put it back in the radical form. For example, I have this right here, 6th root of x to the 3rd. Well, the 6 tells me I'm looking for 6 of something, and I only got 3 x's, so it doesn't seem to help me any. But if I put this in a fractional power form, this would be x to the 3/6. Whatever powers here goes up on top. Whatever your index is goes down below here. Now once I put it in that form, 3/6 is 1/2. So that'd give us x to the 1/2. Or if you put it back in the radical form, that would be the square root of x. So again, sometimes it's necessary to put it into fractional power form temporarily until you can do some simplifying. Now just to refresh your memory a little bit, if you got square root of x times the square root of x. If your indexes are the same, you got radicals, then you multiply what's underneath radicals and put them underneath a single radical. So square root of x times square root of x is square root of x times x. Now remember, we're looking for a pair of somethings. Here's a pair of x's, and I'll bring those out, and they come out as a single x, assuming all my variables represent positive numbers. Well, on the other hand, if you have the cube root of x times the square root of x, you cannot do the same trick because these have different indexes. So I'm first going to put these in the fractional power form, rational exponents. That's x to the 1/3 times x to the 1/2. Now think about where the denominators came from here. These came from the indexes. And over here we said if the indexes are the same, you can just simply multiply them together. So that gives us a clue that we want to get the same indexes or the same denominators. Well, the least common denominator of 3 and 2 would be 6. So here I multiplied the bottom part by 2, so multiply the top part by 2. And over here, I multiplied the bottom part by 3, so multiply the top part by 3. So then, if I put this back in the radical form, this would be the 6th root of x squared times the 6th root of x to the 3rd. Now, since the indexes are the same, we can multiply what's underneath radicals and put them underneath a single radical. So we've got 6th root of x squared times x to the 3rd, which gives us the 6th root of x to the 5th. Now, on some of these simplified expressions with rational exponents, you may have them in fractional power form, like this, x to the 2/3 over x to the 1/5. Then I want you to simplify it. Well, think about how we did it when we had integers there. We had x to a power over x to a power. You subtract a smaller exponent from a larger one. So we got 2/3 minus 1/5. We want to get a common denominator, which would be 15. So I multiply the bottom part by 5, multiply the top part by 5. And that gives us 10/15. Minus, multiply the bottom part by 3, multiply the top part by 3. And 10 minus 3 is 7, so we got 7/15. So we're going to have x to 7/15 where the larger exponent was, which was on top. Remember, we put a placeholder of 1 here. So x to the 7/15 over 1 is simply x to the 7/15. And that's our answer. Okay, let me clear that page off. And let's go on to polynomials and multiplication of radicals. And I'm not going to go over the definition of a polynomial. We'll dive right in with adding, subtracting, multiplying, and handle the special cases. Okay, so if we got 3x squared minus 7x plus 2 plus 5x squared minus 8x minus 2. This is adding two polynomials. Now adding is pretty straightforward. Get rid of your parentheses if you have any. So we got 3x squared minus 7x plus 2 plus 5x squared minus 8x minus 2. And then we're simply going to combine like terms. So here I have an x squared, here I have an x squared. 3x squared plus 5x squared is 8x squared. Here I have an x and here I have an x. Negative 7x, negative 8x is negative 15x. And here I got 2 minus 2. 2 minus 2 is 0, so that drops away. So that'd be your answer. On the other hand, if we had subtraction, now this first set of parentheses doesn't do anything, so I can drop it. So I got x squared minus 7x minus 2. Remember, a negative out in front of your parentheses flips the sign of everything inside. So this will flip the sign of the x squared, the 3x, and the negative 8. So the x squared becomes negative x squared, the 3x becomes a negative 3x, and the negative 8 becomes a positive 8. Well, combine the like terms. X squared minus x squared drops away. Negative 7x and negative 3x gives us negative 10x. And we'll combine negative 2 plus 8, which gives us 6. So that would be our answer. Now if I'm multiplying two polynomials together, what I'm going to do, since I got two terms here and two terms here, I'll take the first term in my first set of parentheses and I'll multiply it times each term over here. So I'm going to have x times x and x times negative 3. So I just follow the lines to see what to multiply together. Then I'll take my second term, the 2, and multiply it times each term in the second set of parentheses. So I have 2 times x and 2 times negative 3. If you learn FOIL, that's FOIL basically. First, outer, inner, last. You can only FOIL when you have two terms and two terms. Well, x times x is x squared. X times negative 3 is negative 3x. 2 times x is 2x, and 2 times negative 3 is negative 6. Always combine like terms. Negative 3x plus 2x is negative 1x or negative x, and then I'll bring it down to minus 6. And that would be our answer. Now, that's multiplying polynomials, but there are some other ways to multiply them too. So let's talk about that. If I had 5x times x squared minus 7x plus 3, this is multiplying one term times three terms. You can't FOIL it. FOILing only works if you got two terms and two terms. So again, I'll use line method. I'll take this term out in front and I'll multiply it times each term inside. The line method will always work in terms of telling you what to multiply together. So I'll take 5x times x squared. I'll take 5x times negative 7x. And I'll take 5x times 3. Well, x the first times x squared is x the third. Remember, if you do not have an exponent there, it's by default 1. 5 times negative 7 is negative 35, and x times x is x squared. And 5x times 3 gives us 15x. Let's take a look at 3x plus 2 times 3x minus 2. Identify and simplify special case products. That's what we're looking at now. Well, we're going to multiply everything like normal here. We got 2 terms times 2 terms. So I'll take my first term, the 3x, and multiply times each term over here. So I got 3x times 3x, 3x times negative 2. And then I'll take my second term and multiply it times each term over here. So I got 2 times 3x and 2 times negative 2. Well, 3x times 3x is 9x squared. 3x times negative 2 is negative 6x. 2 times 3 is 6x. 2 times negative 2 is negative 4. Negative 6x plus 6x cancels. We got 9x squared minus 4. And that's our answer. Now the middle terms dropped away. You're wondering, well, why'd they drop away? Why do they call this a special product? These are called conjugates. That's where your first parts are the same, 3x and 3x. Your last parts are the same, 2 and 2, but the sign in the middle is different. This is a positive and this is a negative. When you got conjugates, all you have to do is multiply your first parts together. 3x times 3x is 9x squared. And your last parts, 2 times negative 2 gives you negative 4. We got one more special multiplication case. X plus 3 squared. What we have to do here is we have to rewrite this as x plus 3 times x plus 3. We cannot just square the x and square the 3. That goes back to what should be called the distributive property of exponents. If everything inside is multiplication division and you're raising parentheses to a power, that's when you can take everything to a power. We don't have that here. We have addition in here. So we have to simply rewrite it this way. And then we can use our line method. Excuse me. So I'm going to take my x here and multiply times each term over here. So I got x times x, x times 3. Then I'll take this second term, this 3, and multiply it through. So I have 3 times x and 3 times 3. Now x times x is x squared, x times 3 is 3x, 3 times x is 3x, and 3 times 3 is 9. Which gives us x squared plus 6x plus 9. Now, as strange as it seems, there's actually a formula for dealing with that special case. It's not one you really have to remember. You don't have to remember the conjugate formula, because if you just multiply it like normal, it's going to be obvious what the answer is. Okay, let me clear those all off. We talked a little bit about multiplying radicals before, and now we're going to explore it a little bit more. This is our last item in this section, is to multiply radical expressions involving multiple terms. Okay, so if I got square root of 2 times the square root of x minus the square root of 2. We have one radical out in front and we got 2 inside. This is a distributive property. We're going to take the square root of 2 times square root of x times negative square root of 2. So we've got square root of 2 times square root of x, square root of 2 times negative square root of 2. Now when you're multiplying two radicals together and they have the same index, you multiply what's underneath the radicals and put them underneath a single radical. So this would be the square root of 2 times x. Positive times a negative is negative, and square root of 2 times square root of 2 is square root of 2 times 2. Now remember, with square roots, we're looking for a pair of somethings. Here's a pair of 2's, so they're going to come out in front as a single 2. I can't do anything with first radical because there's not a pair of anything. So my answer would be square root of 2x minus 2. Now if I had the square root of x plus 3 times the square root of x minus 7, got radicals involved. It's no different. We got 2 items here and 2 items here. When I say items, I'm talking about separate by pluses and minuses. So we'll take our first item, the square root of x, and multiply times each item in our second set of parentheses. So we've got square root of x times square root of x. We've got square root of x times negative 7. And then we'll take our second item here, the 3, and multiply it through. So we got 3 times square root of x, and we got 3 times negative 7. Now remember, when you're multiplying 2 radicals together, you multiply what's underneath them, put them underneath a single radical. So square root of x times square root of x is square root of x times x. Positive times negative is negative, and I'll put the number out in front. Plus 3 square root of x, and 3 times negative 7 is negative 21. Now remember, for a radical, we want to simplify it. This is a square root. My index is 2, so we're looking for a pair of somethings. Here's a pair of x's. They're going to come out as a single x. Now, if you're combining like items, whatever they might be, as long as whatever you're working with is exactly the same except for the numbers out in front. I mean, they can be the same, but they don't have to be. So here we have square root of x, and here we have square root of x. Then you add or subtract the numbers that are out in front. Negative 7 plus 3 is negative 4, square root of x, minus 21. And that would be your answer. Let me clear this off. And our next topic is section R.6, factoring. And actually I got some factoring techniques to write down. Our first method is GCF, and that stands for greatest common factor. Our second method is grouping, and that's when you have 4 or more terms. Our third method is PSD, and that's when you got the form x squared plus bx plus c. Okay, and then our fourth method is key number. And that's when you got to form ax squared plus bx plus c. Our fifth method is dots, and this is difference of 2 squares. And this is when you have 2 terms with a minus between them. Our sixth method is difference of 2 cubes. And this is when you got 2 terms with a minus between them. And our seventh method is sum of 2 cubes. This is when you got 2 terms with a plus between them. Okay, so let's take a look at some examples. We've got 4x squared minus 8x plus 4. Now here we have 3 terms. Terms are separated by pluses and minuses. Now GCF, when we're talking about numbers, we're looking for the largest number that divides into all 3 of them. And that would be 4. So I'm going to factor a 4 out. That's my GCF. Now factor means to write as a product, but as weird as it seems, how we do that is we divide. 4 divided by 4 is 1 with an x squared, minus 8 divided by 4 is 2 with an x, and 4 divided by 4 is 1. That gives us 4 times x squared minus 2x plus 1. We're going to see later on that some of these you can factor down further with different techniques. And this looks like one of them. Now if I had x to the 7th minus x to the 3rd plus 3x squared. Sometimes you have a number in common, like the first example. Sometimes you have x to a power in common. You notice these all have x to a power. Now we want to factor out the most x's we can, but we can't factor out 7 x's if this one only has 2. So it's always one of the smallest exponents. So I'll factor out an x squared. I always tell people if they're learning GCF for the first time to visualize it. You have 7 x's sitting up on a table. Somebody comes and takes 2 of your x's away. Well, you have 5 x's left. Minus, we had 3 x's, somebody came and took 2 over x's, so that leaves us a single x. Plus 3, and we had 2 x's, and somebody took both those x's away, so there's no x's left. And that would be your answer. Now this problem, there's a note that goes along with this. I won't actually write it down in the interest of time. But if you're working with GCF, if your first term is negative, you always factor out a negative. So in this problem, I'd factor out a negative 7, and that would give us x plus 3. Now let's take a look at this example. So we got x squared minus 3bx plus 2ax minus 6ab. Okay, now let me double check myself here. X squared minus 3bx plus 2ax minus 6ab. Okay, that should work in theory. Now our first method we're looking for is GCF. Well, if I look at these, I got 4 terms, but they don't have anything in common. Some have a's, some have b's, some have x's, but all 4 terms have nothing in common. Now 4 or more terms, that tells us to try grouping. Now grouping, we're going to group first 2 terms together and group last 2 terms together. And how you group them is putting lines underneath them like what you just seen here. Now the GCF for the first group looks like they both have an x. So I'll factor that out. And that gives us x minus 3b. Now looking at our second group. We want to factor out GCF. It looks like they have a 2. And looks like they have an a in common. And that gives us x minus 3b. Now our goal was to get these parentheses the same, which they are. So I'll factor out an x minus 3b. And to see what goes in your second set of parentheses, you can come up to the previous step and cross out what you factored out, and what isn't crossed off is what goes in the second set of parentheses, which would be x plus 2a. And that's our answer. Let me clear this off. Then we got x squared minus 22x plus 40. Okay, GCF, greatest common factor, there isn't one. Grouping is 4 or more terms, this is 3 terms. PSD, now specifically what we're looking for PSD is we're looking for an x squared, x, no x, and there's no number in front of the x squared. X squared x, no number in front of x squared, this is PSD. Now with PSD, we take the number at the end, ignoring signs. When I say the number at the end, I'm talking about the constant term here, this 40. We're going to come up with 3 columns. Our P column, the P stands for product. These are all things multiplied together to give us 40. We got 1 times 40, 2 times 20, 4 times 10, 5 times 8. If you're not very good at coming up with these products, you can put them in your calculator. 40 divided by 1 is 40, 40 divided by 2 is 20, 40 divided by 3 gives you decimals, doesn't go into it evenly then. Now the next column is the S column, and the S stands for sum. It means we're going to add these numbers together. 1 plus 40 is 41. 2 plus 20 is 22. 4 plus 10 is 14. 5 plus 8 is 13. And then we have our difference column, D for difference. Subtract smaller from larger. 40 minus 1 is 39. 20 minus 2 is 18. 10 minus 4 is 6. 8 minus 5 is 3. Now we're looking for the number in a middle term, which is 22, which is right here, which means we're going to use 2 and 20 in our answer. Now we got a note on our that'll help us on determining our signs. The note says the larger number in the P column that we are using is always the same sign as the middle term. Well, we're using 2 and 20, so larger of those is the 20. It will always be the same sign as the middle term, which in this case was negative. Now, if the number you circled in the S column, it's S for same signs, both positive, both negative. If the number you circled in your D column, then it's D for different signs. It means one will be positive and one will be negative. Well, the number we circled was in our S column, S for same signs. And if the 2 is, or if the 20 is 2, then the 2 will be, let me say it again. If the 20 is negative, then the 2 will be negative. And that would be your answer. Let me show one more of those. Okay, we got x squared minus 77x minus 240. Let me double check that. Okay. Now, GCF, there isn't any. Groupings 4 more terms, that didn't fit. PST, x squared x, no x, and there's no number in front of x squared. That fits. So PST again. We're going to take our number at the end, ignoring signs. So we got 240. And we'll come up with our 3 columns. So we're going to write all the products give us 240. We got 1 times 240, 2 times 120, 3 times 80, 4 times 60, 5 times 48, 6 times 40, 7, no, 8 times 30, 9, no, 10 times 24, 11, no, 12 times 20. Why did I pick such a big number? 13, I don't think so. 14, no. 15, yeah, 15 times something. That goes 1 in there, then 90, that's 16? I better check that. 15 times 16. $240. Okay, that looks like all of them. So now I'll add them. 1 plus 240 is 241. 2 plus 120 is 122. 3 plus 80 is 83. 64, 53, 46, 38, 34, 32, 31. Subtract them, smaller from larger. 240 minus 1 is 239. 118, 77, 56, 43, 34, 22, 14, 8, and 1. Assuming no math errors. Now the number we're looking for is the number in our middle term, which is 77, which is right here, which means I use 3 and 80. Now our larger number in the P column that we're using, which is 80, will always be same sign as the middle term. Middle term is negative, so this is negative. The number I circled is in the difference column. It means one will be positive, one will be negative. Since this one is negative, this one has to be positive. And that'd be our answer. Now there's a little bit of a shortcut on these. If on your last term it's positive, then it'll be in the S column. If it's negative, it'll be in the difference column. This one, since it was negative, I knew it had to be in the difference column. I didn't even need to create the S column. This one up here. Our last term has a positive here, which means I knew it was in the S column. I didn't even need to create the difference column. That'll help a little bit. In class, I'll always show all three columns. But once you feel comfortable with it, then you can advance a little bit and start looking at that to help you with the signs. Let's take a look at another example. This will be 3x squared plus x minus 10. Let me double check that. 3x squared, 6x, x minus 10. Okay. GCF. Now there isn't one. Grouping is 4 more terms. Nope. This is 3 terms. PSD. It's close, but there's a number in front of the x squared. Can't have a number in front of the x squared for PSD. Key number. Specifically what we're looking for in our key number is we're looking for an x squared, x, no x, and there's a number in front of your x squared. X squared, x, no x, number in front of our x squared. That fits. So this would be key number. Now key number, we're going to take our number at the beginning, what's before x squared, times the number at the end, a constant term, ignoring signs. So I got 3 times 10, which is 30. Now I'm still going to build a PSD table, I just use it a little bit different. We'll write down all products give us 30. We got 1 times 30, 2 times 15, 3 times 10, 5 times 6, guess that's everything. Add them. We got 31, 17, 13, 11. Subtract them. 30 minus 1 is 29, 15 minus 2 is 13, 7, and 1. Now we're looking for the number in our middle term, which is 1, which is right here, which means we'll use 5 and 6. Now we're going to do this a little bit different than the past 2 problems. Before we just wrote down our answer. Now we need to rewrite our middle term using these 2 numbers. Now all of our notes on our signs still hold true. So the larger number in the P column that we're using, which is 6, will always be same sign as the middle term. Middle term up here is positive. So I'm going to have a plus 6x. The number I circled in the difference column. D for different signs. One will be positive, one will be negative. If the 6 is positive, then 5 has to be negative. And then we want to do factoring by grouping. So I group first 2 terms and group the last 2 terms. Looking at only the first group, you see the GCF is 3x. So that gives us x plus 2. Now in the second group, they're both divisible by 5, but even more than that, my first term is negative. And I said anytime your first term is negative, you always factor out a negative. So I'll factor out a negative 5, and that gives us x plus 2. Now our goal was to get these parentheses the same, which they are. So now I'll factor out an x plus 2, and that leaves us 3x minus 5. And that's our answer. Okay, let's take a look at, 9x squared minus 16. Let's see, GCF, there isn't any. Grouping is 4 more terms. This is 2 terms. PSD and key number are both 3 terms. That doesn't fit. Dots. 2 terms with a minus string in it. That fits. So we're going to try difference of 2 squares. Now we try to rewrite it as something squared minus something else squared. If you can successfully do that, that's when you can use difference of 2 squares. Now you ask yourself, what times itself gives each individual piece? For the 9, that's 3 times 3. For the x squared, that's x times x. And for the 16, that's 4 times 4. So we were able to rewrite it as something squared minus something else squared. This is a difference of two squares, and it's just a formula. I'll label what's inside the first set of parentheses as f for first. I'll label what's in the last set of parentheses as l for last. And our formula is f plus l times f minus l. So everywhere I have an f, I'll plug in 3x, and everywhere I have an l, I'll plug in 4. So I got 3x plus 4 times 3x minus 4. And that's our answer. Let's take a look at our next example. X to the third minus 8. GCF. There isn't any. Groupings 4 more terms. This is 2 terms. PSD and key number are both 3 terms. That doesn't fit. Now dots. Difference 2 squares. 2 terms of minus string it. That fits. So we're going to try to write this as something squared minus something else squared. But unfortunately, when you get down here and you start asking yourself what times itself gives you 8, integer-wise, and what times itself gives you x to the third, it fails. So that doesn't work. But you'll notice this says 2 terms of the minus between them, and number 6 says 2 terms of the minus between them. So if difference of 2 squares fails, you come down and you try difference of 2 cubes. It's very similar, except for we try to rewrite it as something to the third power minus something else to the third power. And instead of asking yourself what times itself gives you that piece, you ask yourself what times itself 3 times gives you that individual piece. For example, the x to the third, that's x times x times x. The 8 is 2 times 2 times 2. So we were able to rewrite it in this form, and that's what tells us that we can use difference of 2 cubes. I mean, the form kind of gives us a hint, but you have to actually be able to rewrite it in this form. So I'll label what's inside the first set of parentheses f for first. I'll label what's inside the last set of parentheses as l for last. And difference of 2 cubes is f minus l times f squared plus fl plus l squared. Now everywhere I have an f, I'll plug in x, and everywhere I have an l, I'll plug in 2. So we've got x minus 2 times x squared plus x times 2 plus 2 squared. And that gives us x minus 2 times x squared plus 2x plus 4. And that would be our answer. Grab a drink here, and then I got one more factoring type to look at. Let's take a look at x to the third plus 64. Okay, GCF, there isn't any. Groupings 4 more terms, that doesn't fit. PSD and key number are both 3 terms, that don't fit. Dots and difference 2 cubes is 2 terms of minus between them. We got 2 terms with a plus between them, so that doesn't fit. Sum of 2 cubes, 2 terms with a plus between them. We're going to try to rewrite this as something to the third power plus something else to the third power. And if you can successfully do that, that's when you can use the sum of 2 cubes. Well, x times x times x gives us x to the third, and 4 times 4 times 4 gives us 64. So we were able to rewrite it in that form. Now I'll label what's in the first set of parentheses as f for first. I'll label what's in the last set of parentheses as l for last. And this is going to be the formula for the sum of 2 cubes. So you got f plus l times f squared minus fl plus l squared. Now everywhere I have an f, I'll plug in x, and everywhere I have an l, I'll plug in 4. So I got x plus 4 times x squared minus x times 4 plus 4 squared. So that gives us x plus 4 times x squared minus 4x plus 16. And that would be our answer. I really don't have any time to get into R.7, but I do have YouTube videos out there. If you look under each unit, you'll see the folder for the instructor YouTube videos, and those videos actually go in a lot more depth than I did in the above sections too. So it helps you not only in the ones we don't get to, but in the ones we do cover, because I didn't really maybe have time to show you but one example, and that's not in-depth enough to really grasp it. So watch those videos. Now I'll go ahead and stop the recording, and I'll answer any questions you have.